Hey everyone, welcome back. Have you ever wondered why standardized tests feel so, standardized? It comes down to many factors, one of which is reliability, which is a fundamental quality to check for in any measurement tool. Reliability is simply consistency. It's the assurance that if you take a test today and nothing about you fundamentally changes, you should get a very similar score next week or so. In this comprehensive guide, designed for anyone needing a refresh or an ideally easy-to-digest first lesson, we're going to aim for mastery. We'll break down the theories, tackle the tricky math concepts, and use clear real-world examples to make every psychometric concept click, hopefully. So let's start with the big idea. The backbone of traditional psychometrics is the classical test theory, which provides a simple yet profound model for understanding every score you observe. It is broken down into this formula: observed score, which is represented by X, is equal to true score plus error. Broken down, the observed score is the raw score you physically write down or see on the printout. For example, the student answered 75 out of 100 questions correctly on the final exam. This is the observed score, the 75 out of 100, and the only score that we can ever know for certain. Next, the true score is the hypothetical perfect value. It represents the score the test taker truly deserves, reflecting their actual ability, skill, or trait level that the test was measuring. So essentially, this is the score that they would achieve if the test was absolutely flawless and the taker was perfectly focused. So crucially, the true score is unknowable because flawless measurement is impossible. This is because we have the error. The error puts us in a reality check, so to speak. The error component represents everything that randomly or systematically pushes the observed score away from the true score. It's all the irrelevant, distracting factors, such as nerves, bad luck, guessing, a noisy room, unclear instructions, and more, which we will discuss in depth later on. And so basically, based on the CTT, every single test score you measure is a mix. Your true score and some amount of error are always present in the observed score. And so the entire goal of reliability is just to estimate how big that error component really is. So now that we understand a score is split into two components, the true and the error, how do we use that knowledge to define reliability mathematically? Reliability is mathematically defined as the proportion of total variance attributed to true variance. I know that sounds like a lot, so let's break down this concept to make it less intimidating. So imagine you're a history teacher grading a tough exam for 100 students. You'll see a wide spread of scores. Some are high, some are low, some are just in between. And that spread is the total variance, which is the total score differences. Next, there is the true variance, which is the portion of the spread that is due to genuine differences in what you're trying to measure. So, an example of this would be the actual differences between your students. So let's say student A truly studied hard and knows the dates, while student B barely even opened the textbook. And so the difference in their scores is due to true variance. Next, we have error variance. This is the portion of the spread that is due to random mistakes. So an example of this would be, let's say, student C got a perfect score, but only because they sat next to a smart student and got lucky guessing on a few tricky questions. Meanwhile, student D knew the material, but had a huge fight with their friend right before the test and couldn't focus. And so these random influences create error variance. And so reliability now is the final ratio, true variance divided by total variance. So if your reliability score out of this proportion were to be 1, it would mean that the test is actually flawless. 100% of the score differences are due to actual true difference in their history knowledge or whatever it was that they were being tested on. But this almost never happens. Ideally, you want the score to be as high as possible, but not too high. So let's say an ideal would be around 0.80 or higher, but not too high that it reaches around 0.90 or so. This is because anything above 0.90 could be a sign of redundancy, which means that the test is actually measuring just the same exact thing again and again, rather than actually measuring the whole scope of what you're trying to measure. So 0.80 is good enough to tell you that the test is dependable. Since 0.80 would be equal to 80%, it means that most of the variation you see is because of what the students actually know, not because that they were tired, lucky, or distracted. So basically, reliability tells you, is this test score a true reflection of the person or just a reflection of random chance? So let's go about dissecting error. So we categorize error based on how it behaves and where it originates. So let's first go over the nature of error, first of which is random error. This is the single most important concept when discussing reliability because it is the actual source of unreliability and inconsistency in any test. Unlike systematic error, random error is unpredictable and fluctuates arbitrarily, making it hard to trust the score. As stated, it is caused by unpredictable fluctuations in countless variables or factors throughout the measurement process. So these are the momentary disturbances that affect a person's score one way today and may be a different way tomorrow. So random error can increase a person's observed score in a positive way, which is known as positive error, or decrease it, which is known as negative error, without any warning. So it stems from all the temporary fleeting things we've discussed earlier, such as momentary distractions, slight changes in lighting, a sudden burst of anxiety, a lucky guess, or just a brief lack of focus. But the theory is that over many administrations, these random errors are assumed to cancel each other out. But in any single test, they do distort the score. So ideally, we'll try to eliminate it whenever possible. So how could this happen? Let's have a behavioral example. Imagine a student is taking a reading comprehension test with a tight time limit. So a negative error example of this would be, let's say a student receives an unexpected phone call from a family member during their short break, which makes them feel anxious and distracted for the next 15 minutes. And this momentary anxiety, which you as a test user may not have known, actually leads the test taker to misread the next passage of instructions and answer several questions incorrectly, resulting in a temporary negative error in their score. Now let's go over a positive error example. Let's say later in the test, they come across a very difficult vocabulary question. They make a totally uninformed, lucky guess and just happen to get it right. And so this one lucky guess creates a temporary positive error in their score. So now, because the student's observed score is a mix of these unpredictable varying amounts of positive and negative errors, the resulting score is inconsistent and unreliable. This is because if the student took the same exact test tomorrow, the random errors would have probably been different, and their observed score would likely change, even if their true reading ability or whatever it is that the test was trying to measure stayed the exact same. This inconsistency is precisely what random error introduces. Now let's go over systematic error. This error is a consistent, predictable bias that typically affects the score in the same way every time it's measured. So it is a source of error that is constant or proportionate to the true score. So unlike random error, it still pushes the scores away from the true value, but it does it in a consistent direction across the entire group. So this error is not random. It is usually a bias or a fixed flaw in the measuring instrument or procedure. So it is not the fault of the environment or the test taker, but rather the actual test itself. And since it is the test itself, it affects everyone in a similar way. So systematic error impacts the accuracy of the scores. This is what we call validity, but it surprisingly does not affect test reliability. Why is this the case? Because again, it affects the scores in a consistent way, and reliability is all about the consistency of scores. So even if the test is not actually measuring accurately, it is measuring still in a consistent way. A good analogy of this would be a broken weighing scale. The weighing scale, since it is broken, is fixed on exactly 45 kilograms. So even if you weighed, let's say, 50 kilograms, it will not accurately show your true weight. But since it is fixed on 45 kilograms, no matter what, it will always give 45 kilograms. So it is consistent in that way. It's reliable that it will always give at least that number. So even if it is consistent, it's still not a good instrument. So let's give a actual behavioral example on how this happens in a actual testing environment. So as stated, systematic error usually stems from a flaw in the testing equipment, the instructions, or actually even the environment, which is part of the testing situation that is supposed to be applied uniformly. So imagine an online aptitude test, which is administered to 1,000 applicants. Unbeknownst to the test administrators, the computer program has a faulty timekeeping system that consistently yet predictably deducts 5 minutes from everyone's allowed testing time. Because everyone exactly loses 5 minutes, the overall mean score of the entire group will be lower than it should be. And so the test scores are now biased because they are inaccurate. But since the same 5-minute handicap is applied to every single person, the relative ranking of the individuals is still preserved. So the student who would have ranked first still ranks first, and the student who would have ranked 50 still ranks 50, because the way it's measured is consistent, just not accurate. So the consistency of the scores, which is the relative order, remains unchanged. And so the test's reliability is unaffected by the systemic bias. So now that we know the two types of error, let's explore the specific places where this error creeps into the testing process, known as the sources of error variance. Basically, where did all of these errors that we just talked about come from? So let's first start with test construction error. This is also known as item sampling or content sampling. So the error is introduced by specific items chosen for the test, so the actual test questions, for example. So this type of error measures how much a test taker's score is accidentally affected by a specific tiny slice of content chosen for the exam or test, compared to the entire universe of knowledge that could have been tested. That may have sounded confusing at first, but we could break it down into a more simpler way. So you could think of it like this. So the universe is the entire domain. So this is everything that you could possibly test. So let's say you are an English teacher and you're trying to test your students on grammar. So in the entire universe of that domain, there is every single grammar rule in English. This also spans from grammar rules that is being taught from elementary all the way up to postgraduate school. But in your test itself, you can't test everything within that domain. Ideally, unless you want your participants to go insane, most likely you'd be just testing them on 50 questions, which covers a specific part of that domain. So these 50 questions could cover certain grammar rules that are appropriate for their learning level, such as for high school. But if those 50 questions are a poor or biased representation of what you were trying to sample from that entire universe or domain of knowledge, so this basically means that those 50 questions weren't actually about grammar, you've got yourself a test construction error. So this introduces unreliability because someone's score might be low, not because they lack knowledge, but because the test accidentally hit their weak spot or missed their strong spot in regards to that topic. So here is a behavioral example of how this could happen. The classic scenario for this, as mentioned, involves bad content weighting or poor item representation. So let's say in this scenario, you're a history professor who is crafting a final exam designed to cover all of the 20th century history. So this is the universe or domain, and the domain is huge. This covers world wars, the Great Depression, the Cold War, civil rights, and so on. But there comes the sampling mistake. The professor, perhaps due to personal interest or time constraints, ends up focusing 80% of the questions on World War II and nearly ignores other details such as the Cold War or the 1960s civil unrest. So as you could see now, that within the sample, it's biased to just a certain part of the universe. And so this leads to an unreliable outcome. So let's say there's student A who is super good actually in Cold War, but is only just mediocre when it comes to World War II details. So the result is that they score poorly. Their score becomes unreliable as a measure of their overall 20th century history knowledge. Their true high-level understanding of the entire domain was masked by the test's poor content sample. The test only measured a narrow, disproportionate chunk, making the final score an inaccurate reflection of their competence. In other words, I believe this is something that's very common for most students out there. You studied the entire Chapter 1, but turns out what got tested was just Chapter 2. So now let's move forward and tackle test administration error. This is also known as time sampling error. So this is unreliability that sneaks in due to temporary changing conditions on the actual day or session that the test is taken. So this is all about those random one-off factors that can mess with a person's performance. So this can be broken down into two things. Essentially, this is the environment and the test taker's state. So when we talk about physical environment, these are the external factors in the testing room that might have fluctuated or affected the performance unfairly. So for example, the room is too hot or too cold, the lighting is flickering, there's excessive noise outside, or the desk that the student is using is broken. And so these factors impact the focus and comfort of the test taker. The second category of this is test taker variables. So these are temporary internal states of the person taking the test that aren't really related to the trait being measured. So examples of this would be that the student is highly anxious that day, or they are suffering from a bad cold, they didn't get enough sleep, or they're too tired, or they're preoccupied with a personal emotional problem such as having a family issue. And so this type of unreliability is the basis of time sampling error. Since these conditions change dramatically over time, a student's score today might be very different from their score next week, even though their actual knowledge hasn't changed. So how does this happen? let's have a behavioral example. So let's imagine a high-stakes professional certification exam. For student 1, they had the ideal day or setting. So this student had a restful 8 hours of sleep, their breakfast was perfect, and they even arrived early. Their test administrator also was calm, gave clear instructions, and the room is comfortably quiet. And so because of this, the test administration error would be much lower, and so their observed score will be very close to their true score. On the other hand, let's say we have student 2 who had the unlucky day. This student had a massive fight with their dad that morning and is already emotionally drained. Worse, their specific testing room has a construction crew who is drilling nearby, and their examiner is wearing a distracting, loud outfit and provides hurried and confusing instructions. And so the difference in scores between student 1 and student 2, that is only due to the fight or the construction noise or the confusing instructions, that is due to the test administration error. So the test score for student 2 is unreliable because it reflects temporary psychological and environmental factors, just because they were simply unlucky on that specific day and location, rather than reflecting their true ability. So lastly, let's go over test scoring and interpretation error. This is also known as scorer differences. This is also often called as inter-rater reliability. This type of error pops up anytime a human has to use their judgment to decide what score a performance or an answer gets. So this error measures the consistency between 2 or more different judges, also known as raters, who are scoring the exact same performance or product. So this is super important during qualitative or observational tests, things that don't have a single objective right answer. So this includes essays, art projects, job interview answers, or even gymnastic routines. So for a multiple choice math test, this error is basically 0 or almost non-existent because the machine or the key scores it perfectly every time. So the ideal here is high inter-rater reliability. This means that if rater A gives a score of 8 out of 10, rater B, C, and D should also all give scores that should be close to 8 out of 10. This is because their scoring criteria should be consistent and not wildly subjective or based just simply on their feelings. So how does this happen? Let's go over another behavioral example. So this unreliability happens again when the scoring guidelines aren't perfectly clear, which allows for personal biases or varying interpretations to creep in and affect the score. So let's have a scenario. Imagine a panel of judges scoring dancers in a competition. They are supposed to evaluate on 3 categories: creativity, technique, and presentation. But here comes the bias. Rater 1 personally believes that all modern abstract dance is messy and not real technique. However, Rater 2 loves pushing artistic boundaries and values novelty and abstraction. And so, when the modern dancer gives a wonderful, spectacular, avant-garde performance, Rater number 1 gives the dancer a 6 out of 10. Meanwhile, Rater 2, who again values novelty and the abstract, gives the same exact dancer a 9 out of 10. So this massive 3-point score difference isn't a reflection of any change in the dancer's performance, which was consistent because they all were exposed to the same exact dance. It is entirely due to the scorer's unreliability. This is the personal biases and different interpretations of the scoring rubric by the 2 judges. This introduces error variance into the observed score, making it an unreliable measure of the dancer's true skill level. And that is it for this part of the video. This is just part 1 of our guide to psychometric reliability. If this guide helped you master these concepts, please hit like and subscribe for more psychometric lessons. Thanks for watching again. Bye bye.